Relation, relationship between total entropy and E naught cell. For the moment, we know what is the total entropy. We did that lesson, right? And the entropy, uh, total entropy means if the total entropy is positive, we know that the reaction is taking place, right? If the total entropy is positive, reaction is taking place. Similarly, we know that if the E naught cell is positive, that particular cell is working, right? Okay. Therefore, they have introduced a new relationship, that is temperature into delta S total is equal to NF E naught cell, right? T stand for temperature, and N stand for number of moles. Then F is Faraday's constant, Faraday constant, and S total and E naught cell, you know, right? So for a given temperature, temperature is same, and for a given reaction, number of moles also same, right? Faraday's constant is anyway constant, therefore you can say S total is directly proportionate to E naught cell. Okay, right. So write this one and write this part, what is the meaning of that, and this one. Just let me know if there's any doubt up to now from this small part. Finish copying.
So give few minutes more, please.
Okay. Done. Then take down this point. If E naught cell is positive, then the reaction is written from the left to right in the cell diagram is feasible because S total will be positive. Write that down as well. Okay, done. So based on that, now here, now look at this. This reaction E naught cell is positive. Therefore, we can say already the reaction is feasible. No, 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 no. Right. The reaction is feasible. Therefore, we can consider by looking at the E naught cell reaction, is total also positive. That's what happens. Right? Okay. Simple thing, right? And also this reaction is E naught cell is negative. The forward direction will not take in place, but the backward direction will be taking place. Okay. The last relationship, that is the relationship between equilibrium constant. We are going to learn new term called equilibrium constant and the E naught cell, right? First thing is delta S total will be equal to RL in K, right? But we already know that delta S total will be equal to N Faraday's constant into E naught cell divided by T, what we learned just now, right? Therefore, we can relate these two together, the same thing. And finally, we can say that for a given temperature again, for a given reaction, right? N constant, F constant, T constant, R constant. Therefore, we can say that L and K will be proportionate to E naught cell. right? I can add one more thing here for the same relationship. Ln K will be proportionate to E naught cell, and also it is proportionate to delta S total. That's how the relationship goes. Okay. Please copy that and don't worry about this term equilibrium constant. We'll learn it soon. I mean, right after entropy, we have to learn about equilibrium constant. This is unit 5. Today I'm doing unit 5. So write in the unit 5 note. And in unit 4, in the rates, we learn K. Can you remember that K? One of the K. Hands up who can remember that K that we learn in the rates? Okay. Very good. Yes. Yes, very good. That K is the rate constant. That K rate constant, what we learn, ln K is equal minus EA over R into 1 over T plus ln A, that relationship, right? Arrhenius equation. Here this K is the rate constant. And remember, this is not that K. This is equilibrium constant, right? You are going to learn several Ks here, but the K that we learn in the rate is not this one. Remember, this is equilibrium constant. Okay, if you are done writing, you can go for this question, question number 4. Okay, let's discuss. What is the answer for the first one? Part A. Kaushika, tell me the answer to the part A. EMF. This one, yes. You can see this is the one is going to reduce and this is the one is going to oxidize. So the reduction minus oxidation plus 0.77 minus 0.54. Answer is plus 0.23. මගෙන් අහන්න එපා මම දාන මැසේජ් එක දාන මට ඒ වෙලා තියෙනවා අඩෝ ආන්සර් එක මොකක්ද කියලා. පේනවනේ. ඒ තරමට නිදිමත. Oh, I know that wrong person තමයි. ආන්සර් එක දැම්මා. Calculate the value of equilibrium constant K for the cell reaction. අපි දන්නවා now it's ln K is equal we have to take this relationship millimeter, right? N F E naught cell over RT. So R value is given, T is there, N. In this reaction, yes. Rukaya, how many electrons are involved in this reaction? What is N here? F96,500. We already calculated the inert cell value 0.23. And R is 8.31. And T is, if the T is not given, you have to consider as 298. Niola, how many electrons in this reaction? Very easy. Here Fe3 plus to Fe2 plus. It's only one electron. Therefore, N is 1. Now can someone tell me the answer for K? Latushan, tell me the value for K. Kaushika, what is the answer? Question is, what is the question? Part B. Part B. Calculate the value of equilibrium constant. May tell me the answer for this LNK. Natasha, what is the answer you got? And this is LNK, no? Then shift ln inverse, and you can get the K value. Go.
Sir,
Yes.
sir, I get 8.96 for LNK.
Not LNK. K. LNK is 8.96. So what is K then?
7,806.
Okay. Right. So I hope you get this one. Huh? Right. Done. I'm not going to do this one right now. Next topic. Remember, I didn't do this part. Huh? 6B1. I'm going to skip. And I'm going to do the 6B2 and finish the lesson today. 6B2, sorry, 16B2, redox titration. So from small ages itself, from grade 9, 10 itself, we are learning titration. So the titration that we learned was acid-based titration. Acid is there, alkali is there, you are adding acid to the burette and alkali to the conical flask, and you are adding indicator, and you are doing the titration until indicator change its color. That's the normal titration we need. Right? So there are the neutralization reaction taking place. Right? So the acid do the alkali will neutralize the acid, other way around. Acid neutralize the alkali or alkali neutralize acid. Somehow the neutralization reaction taking place, and you can see the color change during the neutralization reaction. Okay. But this titration, in the redox titration, there will be no neutralization reaction taking place. It's a redox reaction again, right? It's a redox reaction. And redox reaction taking place during this titration. And more importantly, some titrations, you don't have to use an indicator. That is known as self-indicator. Right? Okay. So we are going to learn two redox titration. First one with potassium manganate, right? And another one with iodine thiosulfate. Okay. Redox titrations. Two types we are going to learn, that is KMnO4. Acidified potassium manganate. Here the other one is iodine versus thiosulfate. You can remember this iodine thiosulfate was there in some papers, because this was there in the previous syllabus in unit 1 and 2, right? So acidified potassium dichromate, when the reaction taking place, this potassium, the manganate ion, right, during the reaction, manganate ion will form Mn2 plus. This manganate ion is purple. Sorry. And Mn2 plus is colorless, right? Colorless, or you can say very pale pink. So the color change during this redox titration will be maintained by this KMnO4. Therefore, this titration has its indicator on its own, so known as self-indicator, right? Iodine thiosulfate titration, but remember the color change is not purple to colorless. Huh? I'll tell what is the color change, right? But this is purple and this is colorless. Remember that. So those two are the colors. Here, the indicator is starch. Indicator is starch, and there I can see the color change, that is blue black to colorless. Okay. Now, let's say here you have MnO4 minus, and the other component in the titration is two components are there during this titration. One is Fe2 plus and the other one is C2O4 2 minus. So you are going to add Fe2 plus to this. So MnO4 minus will be reduced to Mn2 plus, right? What we are going to do is, sorry, other way around, sorry, that's my bad. Fe2 plus is here and MnO4 minus here. This is purple and this one is colorless because Fe2 plus dilute solution, colorless. So here purple. This entire solution will be colorless when MnO4 added, and MnO4 will be converted to Mn2 plus, still colorless. And after all the Fe2 plus has reacted, the added MnO4 minus remains without any change. So the endpoint of this titration will be colorless to first permanent pink. Two different stuff. Blue black to colorless, colorless to first permanent pink. Is this clear? You can have a sketch on this, but I will be giving the complete note. Does anyone need to explain this one again about redox titration?
So can you explain again?
Right. So in this redox titration lesson, we are going to learn about two types of titration. That is the titration involving acidified potassium manganate and iodine and thiosulfate. Iodine thiosulfate titration, starch will be the indicator. Color change is blue, black to colorless. In this titration, it's a self-indicator because MnO4 can act as indicator. It has the pink color, purple color and the colorless because MnO4 minus purple and Mn2 plus colorless. So during the titration, usually the MnO4 minus will be in the burette. And we have two types of titration involving KMnO4, that is Fe2 plus and C2O42 minus. Whatever you have used, initial color is colorless. And then endpoint color change will be first permanent pink. First permanent pink means it should be purple, but you know, 1 drop of MnO4 will be in excess of colorless solution, make it pink. Now it's clear, right?
Yes.
Shall I erase?
So can you give a few minutes to
Okay.
complete this?
Yes. Okay. Okay, right. This is the summary. Okay. First topic then, redox titration with potassium manganate. Right. It's better to know all these reactions along with their color changes. right? So remember the potassium manganate is strong oxidizing agent, right? So this is the equation in the acidic solution. This is what happens during the acidic medium. Okay, write down. In acidic solutions, we wrote acidic solution, sorry. In alkaline solution, in alkaline solution, in alkaline solution, potassium manganate will reduce to manganese 4 oxide. Manganese 4 oxide in alkaline solution. Just for your information, here the oxidation number of manganese is +7 and this is +4, right? So there will be only a small change. Compare with the previous one, +7 to +2 means 5 electrons. Okay. Form manganese 4 oxide, comma, which is a brown precipitate, which is a brown precipitate. Which is a brown precipitate, and will interfere the endpoint color. Will interfere the endpoint color. And also, will raise the titer value. Now, in the acidic medium, let's say the titer value will be 20. Make it the titer value will be around, just example, 30 cubic centimeter. Can anyone tell me why the titer value increases when in the alkaline medium? Teshara, what do you think? Niola, why the titer value increase in the alkaline medium? Natasha, what do you think? Why the titer value in the alkaline medium is greater than acidic medium? These are exam questions. The answer is there. No. Can anyone tell me the answer, Pranav? Why the titer value is higher in alkaline medium compared with the acidic medium? In acidic medium, MnO4 will reduce to Mn2 plus, right? So the redox reaction, this will accept more electrons in acidic medium compared with the alkaline medium. Therefore, you need more MnO4 minus for the complete reaction. That's the reason. Write down titer value in the alkaline medium titer value in the alkaline medium is higher than acidic medium because MnO4 minus will not completely reduce in alkaline medium or the alkaline solution. And therefore require greater volume for the reaction to take place completely. Right. Then write down next point. Therefore, potassium manganate 7, or you can call it as potassium permanganate as well. Potassium manganate 7, potassium manganate 7 is almost always used in solutions that are acidic to prevent the formation of manganese oxide. Next point, write down. During the titration, during the titration, Mn2 plus accumulate. Mn2 plus usually we call it as pale pink, right? But since we have large amount and the dilution, so it appears as colorless. Okay. During the titration, Mn2 plus accumulate. But at the dilution used, comma, they give a colorless solution. They give a colorless solution. As soon as, next point, as soon as the potassium manganate is in excess, as soon as the potassium manganate is in excess, the solution becomes pink.
So can you please repeat that?
As soon as the potassium manganate is in excess, potassium manganate 7 is in excess, the solution becomes pink. Solution become pink. and it therefore acts as its own indicator. Yeah, act as its own indicator. So the endpoint is colorless to first permanent peak. Endpoint is colorless to first permanent peak. Colorless to first permanent peak. Is there any doubt up to now? Okay, then the first titration of potassium manganate 7 is iron 2. Titration of potassium manganate with iron 2. So manganate ions reduces, iron 2 will oxidize, and these are the two half equations and the final equation. I think it's better to by heart the complete balanced, full balanced equation, and remember the ratio between manganate to iron is 1 to 5. Right. Now look at this. Fe2 plus pale green, Fe3 plus yellow, and Mn2 plus pale pink. But since we are using dilute solution, entire thing will be considered as colorless. That's why we are taking colorless to first permanent pink. Okay. Copy this one. Okay, right. And these are the steps, right? Pipette and accurately measured volume of 24 cubic centimeter of iron 2 into conical flask, and then add small volume of dilute acid. Make sure that you are going to add sufficient amount of acid. Otherwise, as we discussed, uh, Mn2 plus won't form. Instead, the brown color MnO2 will be formed. So I will interfere the results, plus will increase the titer value as well. Then you're adding potassium manganate slowly while swirling the mixture, right? As soon as you added the potassium manganate, solution will turn colorless because iron 2 will be oxidized. But after all the iron 2 plus is used up, then the next added drop will remain without changing its color. So the solution will turn pink, or the first permanent pink. Okay. Now copy this one. Okay, let's go for calculations now. Right, the titration and the calculation is the important part. Uh, Page number 177, right? Question number 1. Page number 177, question number 1. Let's do this one. Can I know the answers, please? What is the percentage by mass of iron? Pranav, what is the answer? Rukaya, did you manage to find the answer? Right. Right. No one is responding. Iron nail is there. Mass is 1.5 grams. Right. So you are adding this to dilute sulfuric acid. Right. So what happened? Iron become iron 2 plus. right? And then you are going to transfer this solution to 250 cubic centimeter volumetric flask. This is in 250, right? And then 25 of this one taken out and titrate with KMnO4 0.0218 and the concentrate volume is 24.4. Okay. Right. Okay, Pranav. Okay, yes. Now, is this part clear? Hands up those who can't understand the question still. Kaushika, is this clear? What they have done? Latushan, Mivesh, Natasha, Pranav, Rukaya, is this clear? Okay. I assume that the silence is the best answer. Right. So, first thing what we
Excuse
can...
me, sir.
Yes.
Sir, could you explain it again?
Good. The like most important thing in this kind of question is to identify what they have done, right? So here what they have done was they take iron nail, right, and dissolve in sulfuric acid. The purpose of dissolving is to convert iron into iron 2 plus. So all the impurities and the others things will not be converted. The only iron will be converted to iron 2 plus. This iron is added to 250 cubic centimeter, or this solution is added to 250 cubic centimeter volumetric flask and volume up to 250 by adding water. And for this, in this one, only 25 cubic centimeter is taken out and titrate with potassium manganate. That's what they are doing. Okay. So first step, we can find the moles of MnO4 minus because the concentration and the volume is given. So the answer is 24.4 into 0.0218 divided by 1000. We can find the moles. Then if you know the moles of MnO4 minus, you can find the Fe2 plus moles in this 25. Moles in 25 cubic centimeters. What is the answer here? Can anyone tell me the answer?
So the answer is 5.32 into 10 to the power minus 4.
5.32 into 10 to the power minus 4. So we discussed earlier, I told you that MnO4 to Fe2 plus is 1 to 5. So this answer is into 5 will be the number of moles of iron in 25 cubic centimeters. Is that clear?
Yes, sir.
So this, tell me the answer for this one as well.
Two point six into 10 to the power minus
2.6 into 10 to the power minus.
So 2.66.
6 into 10 to the power minus 3. Yes. So the original solution is 250. Therefore, Fe2 plus in 250 multiplied by 10. So 2.6 into 10 to the power minus 2. Okay, is that clear?
Yes.
Pranav, I didn't get you. I put reaction. So now this is the same number of moles of Fe. Therefore, we can find the mass of Fe at last. Mass of Fe. You have to multiply this by the molar mass of Fe. What is the answer? 2.6 into 10 to the power minus 2 into 55.8. It's 1.48, right? Grams. Now that is the mass of Fe, but you have used 1.5. So the percentage will be 1.48 divided by 1.50 into 100 is the percentage. 98.7. Is this clear? Is this clear? None of you are responding. No? Yes. Pranav has got the answer. Yes. Others? Okay, good. That's the first type. Then the second one, titration of potassium manganate with ethane dioic acid. Right? And this is the overall equation. But here the ratio is 2 to 5. Then Right. Hands up who have eaten rhubarb. Who ate that? Rhubarb? No, no one. Okay. So there's a, we can call it as a vegetable called rhubarb is there. It contains this ethanoic acid, right? But in a small amount, right? So this ethanoic acid is extremely poisonous. So when you are dealing with it, you have to use a pipette filler and other safety measures as well. This reaction, another important reaction, this reaction is very slow to start. That means the activation energy is very high. Therefore, we have to heat this reaction mixture before the titration to continue, or like while the titration taking place, you have to heat it. But after some time, you don't need to heat it. As soon as the Mn2 plus produce, Mn2 plus will catalyze the reaction. Therefore, you don't have to heat after some time. So the produced Mn2 plus will act as a catalyst. Therefore, this is known as autocatalysis. So we learned in the previous case self-indicator and here autocatalysis. Okay. Write down. This reaction is very slow. Therefore, this reaction is very slow. Therefore, we have to heat. The reaction mixture to around 60 degrees Celsius. Before starting the titration.
So can you please repeat that?
We have to heat around 60 degrees Celsius before starting the titration. Next point, as soon as the Mn2 plus produced, it acts as a catalyst. It acts as a catalyst. And the reaction speeds up. Allowing to titrate normally and obtain an accurate endpoint. Right. Okay. Allow me to titrate normally and obtain accurate endpoint. Done. Okay. So there the ratio is 2 to 5. Manganate 2 and ethandio at 5, 2 to 5 ratio. Self indicator point was there. Remember. Sorry, self indicator. No, self indicator was already there. It's auto catalyst. Right. We had auto catalyst. Okay. I hope that's clear. The question number 2 is similar to the oxalate one. Right? Therefore, we'll do the question number 2 as well. Do the question number 2. You have to do these questions, huh? Kaushika, you have to send me the answer for this question, huh? Then අහන්න එපා මොකක්ද answer එක කියලා. Kaushika, what is the answer? Even the answer again. Shall I do the question then? Go. Anyone with the answers? Pranav? Latushan? Rukaya? Kaushika? Can I know your answer? Okay, no problem. We have 50 cubic centimeter of hydrogen peroxide, H2O2. H2O2, 50 cubic centimeters. And you are going to dilute it to 1000 cubic centimeters by adding water. And then this sample you are taking of 25 out and titrate with acidified KMnO4. This is the summary. Concentration is 0.02 and the titer value is 23.90. Right. Again, we can find the moles of MnO4 minus. That is 0.02 into 23.9 divided by 1000. Can anyone tell me the value for this? .78, I think. 4.78 into 10 to the power of minus 4. Yes, thank you, Pranav. Yes. Then the next step, moles of H2O2. How to get the moles of H2O2, right? You know, here also 2 electrons are there, similar to the C2O4. Then the ratio will be 2 to 5. Therefore, into 10 to the power of minus 4 divided by 2 and into 5. What is the answer? 4.78 divided by 2 into 5. 11.95 for 1.195 10 to the power minus 3. Okay. This amount is present in 25. Then how much in 1000 this time? In 25. So the moles of H2O2 in 1dm3. 1.195 10 to the power minus 3 divided by 25 into 1000. So the answer is 0.0478. So we got the moles. Yes, good. And they ask in the concentration. So what is the initial volume? Initial volume is 50. So the concentration of H2O2 is 0.0478 divided by 50 into 10 to the power minus 3. You can get the concentration. Mol dm minus 3. Is this clear? Others? Right. Okay, so I did 2 titrations and 2 calculations from those 2. And this one as a homework, question number 3. Okay. We'll discuss the remaining in the next day then. Any doubts from the part that we learned today? Redox titrations, that what we mainly focus on redox titration and redox titration based on potassium manganese. Okay then, that's it for today, Lamai. I'll see you on the next week. God bless you then.
Yes.
Okay.